All right, let's talk about relativity. We've all been there, right? Trying to wrap our heads around those bizarre thought experiments with trains and clocks and lightning strikes. But what if I told you there's a much more intuitive way to understand it? A way that feels less like a brain teaser and more like, well, balancing a budget. Let's dive in. So let's get right to the heart of it with a big question. Time dilation. Is it real? I mean, when we say time literally slows down for an astronaut zooming through space, is that just some kind of optical illusion? A weird quirk of math depending on who's watching? Or is something physically changing for that astronaut? Well, the answer is a huge yes. Something real is happening, and it's way, way simpler than you've been led to believe. Okay, first up, relativity's old story. You know the one. It's all about why those classic examples with trains and lightning can be so dang confusing. They're technically right, of course, but they often leave you feeling like you've just been hit with a paradox, not a piece of physics. So, here's the shift we're making today. On the left, you've got the traditional way of thinking about it. All this talk of simultaneity, inertial frames, Lorentz transforms, it's all very abstract, right? But on the right, that's where we're headed. We're going to reframe the whole thing in terms of conservation, 4D geometry, and simple vector orientation. Basically, we're trading the abstract puzzles for straightforward accounting problem. All right, so here's how we're going to break this down. We'll start with the old story of relativity, then introduce this new idea of the momentum budget. After that, we'll look at how atoms actually keep time, bring in gravity's role, what we're calling a momentum tax, and then put it all together to finally crack the twin paradox. All right, section 2, the momentum budget. This is the core idea, and it's awesome. Think of it as the universe's most fundamental accounting rule. It's super simple. Everything, you, me, this planet, gets a fixed, unchangeable budget of momentum to spend as it travels through space-time. Now, the formal physics behind this idea is this beast, the mass shell equation. And yeah, I know, it looks a little scary, but honestly, don't even worry about the math. All this equation is really saying is that the right side, the mass part, is your total fixed budget. It's locked in. And the terms on the left, those are just the two accounts where you can spend that budget. So let's put that into plain English. Your budget is your total momentum based on your mass. That's the MC squared. It is what it is. You have two and only two ways to spend it. You can spend it on time momentum, which is literally just how fast you're moving through time, or you can spend it on space momentum, which is how fast you're moving through space. That's it. And here is the absolute key to everything. It is a zero-sum game. You can't have it all. The more of your budget you decide to spend on moving through space, the less you have left over to spend on moving through time. It's a direct trade-off. So your clock, your personal rate of experiencing time, has to slow down. It's not a trick. It's not an illusion. It's just accounting. Okay, that's the rule. But why does it work this way? What's the actual physical mechanism that enforces this budget? Well, to get that, we need to zoom in, way, way in. We need to look at how atoms themselves actually keep time. So what do we even mean by an atom's clock? Well, think about what an atom is. It's this beautiful dance of internal parts. You've got electrons zipping around a nucleus. The interactions that hold all that together, they happen at a very specific, unchanging speed, the speed of light. That constant speed of its internal machinery is what sets the fundamental tick rate for that piece of matter. This is so cool. Look at the atom on the left, the one that's at rest. An electron going from point A to point B travels a short, direct path. The clock is ticking along, nice and fast. But now look at the atom on the right, the one that's moving. For that electron to get from its A to its B, it now has to travel a longer, diagonal path. And here's the kicker. Its speed is fixed. It can't go any faster. So what has to give? Time. It just takes longer to complete one tick. The clock has physically, mechanically slowed down. Okay, that's speed, that's special relativity. But we're not done. There's another huge player we have to add to our budget. Gravity. This is where general relativity comes in. And this isn't about how fast you're moving, it's about the environment you find yourself in. So, in our momentum budget model, how do we think about gravity? Well, imagine it as a kind of density to space-time itself. The deeper you are in a gravity well, like standing here on Earth, the thicker or denser the background is. It's like trying to walk through water instead of air. It creates a natural drag, not on your movement through space, but on your movement through time. And this is where it gets absolutely wild. Just standing still, right here on the surface of the Earth, the effect gravity has on your momentum budget
The drag it creates on your time is the same as if you were rocketing through deep space at 11 kilometers per second. That's insane. It's this enormous hidden cost that we are all paying every single second of our lives.
So, yeah, tax is the perfect word for it. Gravity imposes this mandatory, unavoidable tax on your budget. It just skims some momentum right off the top. And that momentum has to come from somewhere. It comes from your progress through time. It slows you down, whether you're moving or just sitting still. Okay, time for the grand finale. Let's take our new toolkit and use it to solve the most famous paradox in all of physics. Because once you see it through the lens of a momentum budget, the twin paradox stops being a paradox at all. It just becomes an accounting problem. You know the setup, right? One twin stays on Earth, the other blasts off into space on a high-speed round trip. When they reunite, who's older? The old way of thinking leads to confusion. But with our new budget tools, the question isn't just who's younger. It's, okay, let's see the expense reports for both of their trips. And this table just makes it all so clear. Look at the top line, the speed demon. That's the classic version. They go super fast, spend a ton of their momentum budget on space travel, and come back younger. No surprise there. But check out the second line, the Sunday driver. This is fascinating. What if the twin travels really slowly, but goes to a place with zero gravity? Well, they've escaped Earth's heavy gravity tax. Their clock actually ticks faster than their twins back on Earth, so they come back older. And of course, if you go dive near a black hole, the gravity tax is so huge you'll come back way, way younger. It all depends on the path. So the big takeaway is this. There is no one simple answer to the twin paradox. It's not a paradox, it's a math problem. The final outcome depends entirely on the total path each twin took through space-time. You have to add up all the momentum they spent on speed and then subtract all the momentum taxed by gravity. Once you do the books for both twins, the confusion just vanishes. And this really brings it all home. This is the whole point. Relativity is not about optical illusions. It is about the rigorous conservation of momentum in a four-dimensional geometry. It's not a magic trick. It's a fundamental rule of the universe, as solid and real as gravity itself. It's just accounting. So I'll leave you with a final thought to chew on. Right now, at this very moment, you're sitting on a planet that's spinning, which is orbiting a star, which is flying through a galaxy, all while paying that massive constant gravity tax just for being here. So, what does your momentum budget look like? How are you spending your fixed allowance of motion through space-time?